Hello, and welcome to this video where we're going to look at forces of motion, more particularly Newton's third law. This particular video will align with a worksheet that's been given to you by a teacher. It deals with a light scale pan situation. Okay, so very quick video so that you can make notes with that workbook page, and at least then you've seen a possible extended example of how Newton's third law works with connected particles. So what we've got here is a light scale pan. And in this light scale pan, it's attached to a vertical light inextensible string. The scale pan carries two masses, A and B. Okay, the mass of A is 400 grams, and the mass of B is 600 grams. A rests on top of B. The scale pan is raised vertically with that acceleration. So there is the weight of mass A. Obviously, weight is given in kilograms, so 0.4. Mass is given in kilograms, so 0.4 of a kilogram times by G, which is 9.8. So the combined that weight of G of A is 0.4 G. There's the weight of B, which is 0.6 G. Clearly, this is going up, so there's an acceleration of 0.5 meters per second squared. Right, so what is going on here? So for part A, they're asking us to find the tension in the string. Now, the advice given in this particular question, for this particular example, is to find the tension in the string, you should consider the system as a whole. Now, why do we do that? When you've been taught this whole concept of Newton's third law and connected particles, it's good to take the system as a whole when you want to find an overall force that's causing a movement. Okay, when you want to find individual forces, good to sort of zoom in on particular objects. But when you want to find an overall force that's causing a movement, let's consider the system as a whole. And when you consider the system as a whole, it's moving upwards. So if it's moving upwards and it's accelerating upwards, then it's obeying Newton's second law, which is F equals ma, and F means resultant force. Now, if you resolve vertically, let's just look at what's going on vertically. We've got tension going up, and we've got these weights going down. Now, in this situation, there is no normal reaction as the pan is not on the surface. Okay, so if this pan was on the floor, then there'll be a normal reaction force going up. But because the pan is in the air, there is no normal reaction. So let's think about this. You've got these forces going up, which is T, and you've got these two weights going down. The resultant force will be the difference of the T and these weights. Okay, so the resultant force will be T minus 0.4 G minus 0.6 G, and that's equal to ma, which is 1 times 0.5. 1, where does that come from? 0.6 G plus 0.4 G. Yeah, which is obviously 1 G, which means a combined mass of 1 kilogram. Yeah, mass A is 400 grams, mass B is 600 grams. If we consider the system as 1, that's 1 kilogram, times by A, which is 0.5. You then rearrange to get your value of T, which is here. So that's the answer for part A. Find the tension of the string, 10.3 newtons, okay? And that came from considering the system as a whole. Now, let's see what happens in part B. In part B, they're asking us to find the force exerted on mass B by mass A. Now, if you look at what they're asking you for, they want what is the force of mass A on mass B as this situation is happening, as this scale pan is going up. Now, it's quite simplistic for students to just think, oh, it's just the weight of A, 0.4 G on B. It's quite simplistic to think that, but actually, we've got to think a bit carefully here. What we can't do is the students will look at this and go, okay, force exerted on mass B by mass A. So they'll focus on mass B. But actually, we can't consider mass B on its own at this point. The reason is that the scale pan is also acting on mass B. Yeah, there is clearly a contact force of the scale pan on B, and we don't know the magnitude of that force. But by Newton's third law, what we can say is that the force exerted on mass B by mass A will be the same as the force exerted on mass A by mass B. Okay, so by Newton's third law, we can say that. So actually what we can do is in part B, we can focus on mass A. And by doing that, let's think about resolving forces on A. Let's focus on A. We've got the weight, which is 0.4 G. we've got this force here, which is the reaction force of B on A. And as we know, this is also accelerating by 0.5 meters per second. So we can use F equals ma. And what is the resultant force? Well, if you take up to be positive, then the resultant force would be R minus 0.4 G. That's the resultant force. And that's equal to ma, which is 0.4 kilograms mass for the block A times by 0.5. So the actual answer is 4.1 newtons. That is the magnitude of the force from B acting on A. Okay, and therefore 4.1 newtons would be the force from A acting on B. Because of Newton's third law pairs, they will be the same. Yeah, because they're staying together. Okay. Right, part C, find the force exerted on mass B by the scale pan. So now that we have to involve the scale pan, let's involve or consider the forces acting on mass B. So I'm going to draw a diagram for B, and we're going to think about what forces are acting on B. We've got the weight. We've also got 4.1 newtons acting from A on B, and we've got a clear contact force of the scale pan on B. And that is also accelerating. So if we resolve forces on B, then we do F equals ma. It's obeying Newton's second law. And we take up to be positive. So any force upwards, which is S, and you subtract any force going downwards, minus 4.1 minus 0.6 G equals ma. And you solve to get S. Now, this type of question can be tricky to get the hang of. And in reality, it's very unlikely that this sort of question can come up. However, just for the purpose of knowing about it, it's good if you can write this into that workbook page, which has been given to you by your teacher. Okay, that's the end of the video. And I'm hoping that you've understood this concept thoroughly.